from an attacker VM, we can find and leak unknown victim VMs and their private keys. So at least Google thought this was important research because they granted this more than $150,000 bug bounty for it, which was quite cool recognition of the work, I think. And in the end, the goal is going to be to improve microarchitectural security. So that's what I mainly want to talk about today. Now, let's do a quick Git blame because I did not do this by myself. There's a bunch of people I worked with. So from the FUSEC research team, there was me together with Thijs, Mahesh, Dave, Herbert, and Eric. There was also Marius, the blonde guy from the previous talk from the University of Birmingham. And then from Google and Amazon, there were Alexandra, Eduardo, Federico, Claudio, and Moritz. And all these people together worked towards the final product, which was the exploit, basically. But I want to, like I said, talk maybe a bit more on a high level about microarchitecture security. So I would say a quick timeline of it looks like this. There was what we by now call traditional microarchitectural attacks. Examples of which are, for example, that you try to do a cache side channel attack against a crypto library to leak its secrets. And then in 2017, there was a major highlight in the research field, I would say, because there was the discovery of Spectre and Meltdown. And basically, the essence of what we learned via those attacks is that data that you acquire on the microarchitectural level, so not the software, but somewhere in the hardware, if you gain as an attacker access to data there, you can actually make it into a knowledge about the information itself. So like you can turn it into real knowledge and not just some microarchitectural transient secret that disappears again. So after Spectre and Meltdown, many more of these kinds of attacks with abusing speculative execution and such came to light, all with the same ID. We're going to take a look at one more today, which is called L1TF. And the end result is that now in 2025, we have many attacks and there's many so-called spot mitigations, which are mitigations that really try to target a particular attack, and usually mostly it's symptoms and not really the root cause. And this has a good reason, because I want to put a scale on the screen. There's no such thing as perfect security, and you have to have some kind of a balance between security and what you are willing to pay for it. So where there's security on one side, in this particular research field, like high-performance CPUs, performance really is not in line exactly with microarchitectural security, because many of the vulnerabilities that we saw, like for example Spectre, directly stem from performance optimizations that were done, like speculative execution. And so mitigating the root cause of the issue would directly remove the performance optimization, so costs you performance. So you have to have a balance. And moreover, there's other things to take into account, right? For example, the complexity of your mitigation. If it takes a lot of effort to develop it or a lot of effort to maintain it, maybe at some point you say it's not worth the risk anymore. So it's good that people did this kind of risk assessment, but I would say that by now the security landscape of the microarchitectural security is not super good, in the sense that there's still attack vectors all around which might get exploited. One example is, for example, Spectre. You can still do that if you find a really good gadget. Today we're going to take a look at another version, which is a combination of two known vulnerabilities, half Spectre, a slight dumbed down version of it, and L1TF. And now, the thing that I started to dislike a little bit about this picture in the last few years when I talked to people about it, many people, maybe I felt like, didn't do the risk assessment all too well, because I always heard some feelings of these kinds of attacks that, for example, they're complicated because they involve like cache side channels and all this speculative execution, which sounds very insecure or maybe uncertain to many people. People would say to me, oh, but doesn't it only work in a lab setting, these kinds of attacks? It only works on particular CPUs. What about if there's noise? Like if there's other programs running, doesn't the cache side channel not work anymore? These things are very slow, I heard. So there were many, I would say, criticisms I heard, which were more like vague arguments, I would say, that I heard from people, which actually I think stem from valid concerns. But I don't know if they should really turn the tide on the risk assessment people make in the end. So we're going to come back to this later. And so the goal basically of this research is to give a good example of a real exploit and how it would look like, and showing that all the stuff on the bottom or on the top here maybe is not a valid reason to discard these attacks as not threatening. Okay, so the exploit, this is what we'll talk about today. We named it L1TF Reloaded because it's a combination of a bug named L1TF and half Spectre. I'll talk about those later. And this is what it does in the end. In the end, we deployed this attack on both AWS, so the cloud of Amazon, and Google Cloud. And on both, we were able to get an arbitrary host memory read primitive. So any data that the host can see, we can see, which is obviously not good. And then actually only on Google, we are also able to turn that into an arbitrary guest memory read. So from other VMs, read their data. So that's the high level of what the attack does. Let me talk a bit about the setup. So we targeted 3 clouds, you could say. One of them was just a local Skylake server in our lab. So we had full-blown access to it, physical access to the hypervisor, everything, which was nice for debugging. And then there was the Google Cloud and the Amazon Cloud. And on both, we rented dedicated hosts. So what this means is you rent an entire physical machine, and the cloud says to you, you will own the only customer on this machine. And now you can put VMs on there. There will be no other customers on there. The reason for this is that we wanted to do this research ethically. So, of course, we don't want to actually launch a VM, start doing these attacks, and gain access to other people's data. And this way, we ensure that it's impossible for us to ever see anybody else's data. The other side of the coin is that you could say, but then is this a real attack? Because now a dedicated host, there's never any other customers on your machine. That's why actually we talked to all the people from Amazon and Google up front. We actually also contacted some other cloud providers, but it's hard to get these things fully set up. So in the end, only Amazon and Google were in this research, where we said, we want to attack your cloud. How can we do it ethically? And they told us, rent a dedicated host, because actually all the hardware and software and all the configuration and let's say the particular kernel they're running, the particular mitigations they enable against these kinds of attacks, etc. They said it's all the same, whether you do a dedicated host or a shared host. So they told us if you can exploit this and leak data from one VM to another, you can also do it with other customers' VMs. So this is both ethical and realistic. And on the realistic front, I would like to add that actually this list of people who were involved, you should cut it in 2, I would say. There's the bottom part who were kind of the defenders, you could say. And so they were really there to say, we're going to do this exploit on your cloud and you're allowed to do it. And this is the best way to do it sane or ethically. But they did not give us any more information. Whereas on the top is the attackers. We were really black box in all the other senses. So we did not have any information from them on what maybe an internal Google employee would have. We did not have any access to the hypervisor or the machine. All we did was that they gave us free credits that we could spawn VMs on my own Google account. I could spawn VMs for free with the normal web API, and all I got was a terminal into my VM, and that was it. So we were really black box attackers. And because I wanted to show these attacks can be done for real, this was important to emphasize. Now let's go to the threat model. What is the attacker going to do? So we have a red attacker VM on the left, and there will be a blue victim VM on the right. At the bottom in gray is a Skylake CPU. The L1TF vulnerability that we're going to exploit actually is only there in old Intel CPUs, because by now they patched it. So you have to have for example, Skylake server to do this exploit. Now, is this hard? It does limit what machines you can attack, but on both Amazon and Google, you can just pick your machine instance to be one that is backed by this. So this was actually very easy. Secondly, the hypervisor on top is KVM. Both Google and Amazon run some version of KVM. We don't know exactly what or what patches they have, but some KVM thing. The exploit technique that I'll tell you about is actually general, independent of the hypervisor. But our exploit targets this one, specifically KVM. Then there's the victim VM. In blue, it will run either a default Debian or Ubuntu distro with the corresponding default Nginx web server on top. And the Nginx server will be configured to HTTPS, so it will have some private key, the private TLS key of the web server, and that will be our goal to leak. So we just picked some realistic, small secret that if you leak it is very bad. So for example, if you leak it, you can impersonate this web server. You could leak any other data also, but we picked some example. And then the rest of the talk, we'll talk more about the cloud on the left of what is this exploit doing. So first of all, half Spectre. So half Spectre is a sort of dumbed down version of Spectre, which is an attack that exploits speculative execution in CPUs. What this means is, suppose that this is a piece of hypervisor code, and that the attacker controls the variable x. Then when the CPU executes this code, whenever it hits the if statement, it will not actually wait to figure out whether x is smaller than the size of a before it starts to compute the rest, because that would be slow. Instead, it speculates on what the value of that branch will be, and it will just execute whatever code is behind it. So for example, if the CPU speculates that usually x is small, then it will just go into the if statement and execute y equals a of x. So what does this particular snippet of code then enable an attacker to do? It enables the attacker to pass in a very high value of x, and therefore let the CPU speculatively index this array A with a very high offset. So what it gives the attacker is a speculative load during speculative execution. So you can choose some piece of memory and let it load it into the CPU cache. Well, what do you want to do with this? Well, on its own, this gives you nothing. There's no leakage here. It just puts something in the cache and that's it. But we'll see how we abuse it later. Second of all, there's L1 terminal fault. This is really more a CPU bug, you could say, although we only realized it after Spectre and such. Suppose you're in a VM and you have a pointer, and the pointer is backed by some page tables. So here I depicted the page tables, and then there's the guest physical memory, and there's a physical address in the PTE that says your pointer points to this physical memory. Now, as an attacker, what I can do is I can set the non-present bit of this page table entry in my VM, and then I can dereference the pointer. And the question is, what happens? Well, now the page table entry is not valid anymore, so it will raise a page fault. However, on the microarchitectural level, what will happen is the physical address in the PTE is still taken, and it's used to index into the L1 data cache, but now not interpreted as a guest physical address, but as a host physical address. So what happens is, on the microarchitectural level, the CPU will pass to the pipeline whatever was the value at that physical address, host physical address, to instructions of the attacker, and then the attacker can do some, for example, cache side channel techniques to actually get it out into the real software world. Like I said, since we know of Spectre and such, whenever you leak something microarchitecturally, you can also leak it architecturally. So what this gives you as an attacker is the primitive. I pick a host physical address, I put it in my PTE, I dereference the pointer, and then the CPU will say either nothing, if it's not in the cache, the L1 data cache, or it will give me the data, if it was in the L1 data cache. Now, this is bad. So how would you, for example, exploit this? Suppose you have a physical core with one logical core and an L1 data cache, and there's a victim CPU running for a while. Time goes to the right here. Then you context switch to a attacker vCPU, and then all the victim's data would still be in the cache, and you can just read it out. So people said, let's fix this by flushing the L1 data cache upon every context switch, so that there's no interesting data left anymore. This would work except for the case that if you have SMT, so hyperthreading, you'll have two hyperthreads that share your L1 data cache simultaneously. So now if you have a victim virtual CPU running on one hyperthread and it's using the cache, then while it's using the cache, simultaneously the attacker hyperthread can just leak it out. So people realized this also, and they said, okay, this is not good enough. What we should do is not allow this situation anymore. This is called core scheduling. So the hypervisor will ensure that no two distrusting VMs will ever run on the same core simultaneously. So in this picture, you see there's two blue VMs running together, or threads of a VM, and there's two attacker vCPUs running at the same time, but never intermixed. This also would work, except for a last case which is not covered yet, and that is the hypervisor itself. So what the residual attack surface now is that suppose there's an attacker vCPU running on both threads. The top one, what it will do is just enter the hypervisor by doing, for example, a hypercall or something like that. And the hypervisor would put its data into the cache, and then a sibling thread on the other hyperthread of the attacker can leak it out simultaneously. The fix for this would be what we call strict core scheduling, which is saying let's not schedule also the hypervisor with any VMs together. But that has really bad performance and complexity issues, so people did not want to deploy that. And the reasoning was the hypervisor's data is not that secret. It's not that sensitive. Probably it's just computing on data of the attacker VM itself anyway, so it can just leak some metadata of the hypervisor and its own data. So this is not a big security risk. But remember the other bug we're going to exploit. So how do we get to interesting data here? Half Spectre. So now suppose that there's a half Spectre gadget in the hypervisor, which, remember, gives the attacker the capability to let the hypervisor load any data into the L1 data cache. And by now, with L1TF, we have the primitive to leak anything out of the L1 data cache. So what will now happen is the attacker vCPU will go into the hypervisor, trigger the half Spectre gadget to load whatever data it wants into the cache, and then simultaneously we'll have a hyperthread that is doing L1TF and leaks it out of the cache. So this is the attack we implemented. It's also an attack that has been talked about, or at least this is on public mailing lists already like 8 or 7 or 6 years ago or something. It's also explicitly listed as a problem with this defense. But apparently, this was not good enough reason yet to enable more defenses. Because, for example, both AWS and Google deployed this as their defense. We'll see, AWS did actually something more, but that's for later. So what the attack does is exactly this. So we can now fill in the exploit cloud. It consists of 2 vCPUs. One of them is doing L1TF constantly, and one of them is doing half Spectre. And then maybe you wonder, what does the actual half Spectre gadget look like? Well, here it is. Obviously, everybody in the room now thinks, yeah, that's a half Spectre gadget. But maybe let's have a quick go through of it. So this is a KVM function called KVM sched yield. It is a hypercall handler. So the VM can request this code to be run, and it can pass an argument. The argument is dest ID. So this is fully attacker controlled. And then at the bottom here, this dest ID is bounce checked against max APIC ID to be small. And then after that, so this is the branch that we speculatively bypass on the microarchitectural level. We do an array index with dest ID as an index. So this should remind you of the half Spectre gadget before, and so we can let this array index pull any data we want into the cache. Okay, so what this gives us in the end, all in all, is an arbitrary read primitive into KVM's address space. So any data that the hypervisor KVM can load, we can now read. Here's a nice plot of how good we leak, and spoiler alert, the answer is quite bad. On the x-axis here, there is the time spent per byte. Meaning, if we spend, for example, 1 second trying to leak 1 byte, or 10 seconds trying to leak 1 byte. And on the y-axis, we report the byte error rate. So how did there occur an error in your byte? And so we see that on our local server and AWS, when we pick, that's what our exploit does, 1 byte per second leakage, there's about 5% error rate or something like that. Whereas on Google Cloud, they do something funny. They deployed some extra sort of mitigation-ish things that slow it down a lot. So there actually, when we leak 1 byte per second, half of them are wrong. So you could say this is quite a bad primitive, right? I mean, I can read faster letters on a piece of paper than this leakage primitive can read it out of the CPU. But as we'll see, you can still build a real end-to-end exploit that is impactful, even with a very bad leak primitive like this. Okay, so the real problem is, how do you find interesting data? Because remember, we want to leak this key of Nginx, but for example, on the machine that we exploited on Google Cloud, it has 800 gigabytes of physical memory. So if you're just gonna, read it, try to read it all and find the key, it's gonna take you many, many centuries. So that's not an option. The real thing that we're gonna do is pointer chasing. So I'm gonna walk you through the exploit now. Remember, it starts without even knowing the victim VM, right? We're just one attacker VM, we don't know anything about the victim. And what we're going to abuse is the fact that the host kernel has all the metadata needed to figure out who the victim VMs are. The host kernel knows what VMs it's running. So what we do is, when we leak, we start leaking at the gadget. The gadget has some nice pointers that we can start chasing. And we start to do a pointer chase through the structures that the kernel has. So the kernel keeps a bunch of metadata and a bunch of structures, and they're all pointing towards each other. So we start following those pointers to figure out what the host CPU is doing. So for example, there's a doubly linked list of all processes running on the host. You can just traverse it. That's what our exploit does. And it just prints all the processes running. And at some point it will figure out, hey, there's a VM here. So this is what it does. It just pointer chases through. And at some point it will figure out, hey, there's a VM. Then it will look up some more data and figure out, it's running actually this particular kernel. And then what we do is we go leaking in the guest kernel, because the guest kernel knows what processes it is running. So then by pointer chasing in the guest kernel, we're going to, for example, just print all the processes it's running. That's what our exploit does. And whenever it finds a process called Nginx, it goes to its metadata. And for example, figure out where is its heap, etc. And at some point know, okay, here's the key, and leak it. So this is what the exploit does in the end. There's two, let's say, challenges left. Remember that actually our leakage primitive is really bad, right? It makes errors all the time. And if you make one error throughout this whole pointer chase, then you lose track of the trail. So the chance of you hitting the end, if your pointer chase is really deep, which it is in our exploit, it's like 200 deep or something like that, your chance is like 0. So instead, what we have to do is what are called chase and check. So every time you leak a pointer, or most of the time, you try to check if you're in a sane state. So you look around in the kernel where you are and you check, does this look like where I expect to be now? So you look for some magic values, you look if some pointers are there that you expect to be there, etc. A simple example could be, if you traverse the doubly linked list, every time you chase a next pointer, you also leak the pref pointer and you check, does it point to my last location? And so this is what you do. You chase and you check, you chase and you check. And if you ever see a chase and you see an insane state, then you go back. So here the check fails and we backtrack and leak again. So this makes sure that our exploit, although it makes a lot of mistakes, it can recover from its mistakes. And then hopefully next time you leak, it works. Okay, so this is one thing we do. Second thing we do is the complication of address translation. Remember, the host virtual address space actually has some page tables to translate it into host physical memory. But the pointers we leak are are virtual addresses, whereas our leak primitive gives us the primitive to leak physical memory. I can tell the CPU, here's a physical address, give me the data, please. So what actually our exploit does is we implement a page table walker on top of our leak primitive to, whenever we see a pointer, translate it to a physical address, and then we can chase the pointer to leak its data. The picture is actually a little bit more complicated, of course, once we start leaking in the VM, in the guest VM, because then you have guest virtual address space translated by the guest page tables to guest physical addresses, but those are translated by the hypervisor via extended page tables to host physical addresses. So our exploit also has a two-dimensional page table walker built on top of the exploit, the leakage primitive inside. And all in all, that gives us L1TF reloaded, the exploit that just leaks the key. Now, does it work? Well, when we ran it on AWS, it only worked partly. So this part all worked, leaking all the structures in the host kernel. But once we arrived at the guest, we didn't see its data. The reason for this is that they deployed some extra defense in depth to protect guest data, and we'll see that later on. The results on Google were, well, I guess as you already knew, it worked. So the whole thing, as I explained, it works. And some results, for example, when we ran this on the exploit 28 times on a bunch of different hosts with victims with independently generated secrets, it completed 25 times, and all of those 25 times the exact correct key was leaked. So it's not like one bit maybe was missing or something, all of them are exactly correct. And the average runtime was 14 hours. So, and I should mention, actually 11 of the 14 hours are like an initial setup stage, where we need to brute force some stuff at the start. So if you would have some more VMs on this host, leaking their keys just takes like 2 hours more for each or something like that. I would say that's quite doable, especially as you can just also just spawn 1,000 VMs, right? We don't need to know our victims. So you could just launch this at scale and start leaking keys from whoever co-locates with you. Lastly, the picture is actually a bit more realistic like this. So we had an attacker VM, a victim VM, both just occupying one core. But the server had like, I don't know, 48 cores or something like that. So most of the server was idle. So you could say, but this is an idle system, maybe it's easier then. So next what we did is we filled up all of the cores with noise VMs that try to generate noise in a bad way. You can read our paper if you want to know the details, but for example, one of them is doing a lot of threads that just traverse a lot of memory all the time to constantly trash the last level cache. Things like this. I/O, traffic, whatever. So a lot of noise. And then we ran the exploit again. So when we ran it 10 times, it completed 10 times and we got 10 correct keys. Average runtime was 15 hours, which is not like the standard deviation here is like 8 hours. So it's like the same time. So the conclusion is the noise doesn't matter. Okay. Lastly, mitigation. So what did actually AWS do, and by now Google? So AWS deployed what is called exclusive page frame ownership. Basically what they say is we try to unmap memory from KVM such that even KVM cannot see the guest data. This is like a defense in depth, which they didn't even, I think, specifically think about L1TF when they did this. They just thought for a very broad class of attacks, it's nice to not trust our own hypervisor to be secure. So let's not give it access to the data it doesn't need. I think that's a really good design approach. And Google by now actually deployed a very similar defense in response actually to L1TF Reloaded. It's a defense that they've been working on for many years already, but now they deployed it on their, let's say, Skylake part of the fleet. It's called address space isolation. And again, it tries to unmap memory from the hypervisor such that even the hypervisor cannot see the data. I could talk a whole hour about defense techniques like this and all their nuances and etc. But this is not the talk for that. But I would say these are good, proper defenses that really don't only try to tackle the symptoms of the attacks, but really try to, at the design level, think how can we make our design of the hypervisor more secure against a whole class of attacks. So that's good that industry is moving towards this. Okay. So now I want to conclude. I would say the RAIN project, I see it as a motivating example, hopefully, for the research field of microarchitectural security. I think the attack techniques that we use, so for example, side channel attacks and speculative execution, I agree that they are advanced, they are brittle, they're unreliable, they're slow, they're inaccurate. So I agree with the fact that they are quite bad. But I think what hopefully this project shows as an example is that the exploits that you can build on top of them can be very robust, very reliable, right? Despite noise, you can just run the exploit many times and it will give you the key. Very accurate, always the correct key. It's reproducible. Both people from Google, from Amazon, and independent researchers already cloned our repo and said, yeah, it works. It's scalable, like I said, right? We don't even need to know the victim. You can just launch 1,000 VMs and start leaking keys everywhere. It's stealthy. In a very essential sense, these kinds of microarchitectural attacks are stealthy because they don't leave any software visible trace. It's all speculative execution, so you leave no trace. And indeed, none of the monitoring systems of both Amazon and Google ever flagged our exploits as something malicious or so, although our exploit has been running for many, many compute weeks for evaluation and development and whatever. And lastly, I think hopefully I convinced you today a bit that these kinds of exploits are realistic. You could build them and they would work. So yeah, that was it for me. If you want more info, there's a link over there, or just Google like fusec space rain. And I'm up for questions if there's time for that.
Thank you so much. Do we have questions in the audience? Yes, we do. Just give me a sec.
Hi. For the pointer tracing into the guest VM, were you testing against a range of Linux versions or just a static one? And if you were testing against a range, how were you finding stuff which worked across versions?
Sorry, could you repeat one more time?
For the guest VMs, for the pointer chasing, were you testing against a range of Linux versions? And if so, how were you finding pointers to chase which worked across versions?
Yeah, so good question. So, no, we just did 2 versions. So, we support like the latest Ubuntu and the latest Debian. And you would have to change the exploit a bit to support more versions. We did not implement that. But I think that would be very little work compared to if you have the thing already running, then you could support many. For example, I started with Ubuntu, and then I thought, what will be the next one I support? I just support the default VM that Google Cloud gives you, which is the Debian some latest version. You should hardcode more in the exploit to support more.
All right, we have another question on that side.
Thank you, nice talk. So my question is basically a follow-up question. So I understand that this does not apply to basically the victim VM, but how does it apply to like the hypervisor? Is that also transferable between different hypervisors? So can you basically use the same pointer chasing primitive on AWS and Google Cloud, or is that somehow different?
No, that's also different. So indeed, for both the AWS host kernel and the Google host kernel, we reverse engineered some like offsets in all their kernel structures to know, okay, this pointer is at offset 58 and this pointer is at offset 40, and they can change a little bit. I think the good news there is that they don't change their kernel much, so that's quite stable. Like across all the months I was doing this research, it never changed ever anywhere I saw.
Okay, and this, you basically did all of this from like a black box perspective, so you couldn't modify the AWS or Google Cloud hypervisor basically. So you had no, you didn't have the source code there.
Yeah, I can actually even show you. You can now see how messy this thing is. So for example, I had a slide at some point. Can you see this?
Yes.
This didn't fit the time I thought, but so what I would do, sorry. So what I would do, suppose you have a kernel structure like this. So I have a KVM local APIC and I have a pointer to it, and I want to chase to this virtual CPU highlighted, and I want to know the offset. Then what I would do is literally just on a local machine, like our local setup, I would just dump the data structure. It looks like this. And I know the pointer is the highlighted one. And then I use my leak primitive on AWS and Google to dump it also on their clouds. Then you get this. And well, I think everybody in the audience can guess what vCPU here is. The answer is hex 98.
Okay, great. That answers my question. Thank you.
Thank you. Do we have another question? All right.
Maybe just quickly, you had that one slide with the error rates on the side channel. Can you say what the mitigation was that Google Cloud implemented for basically having higher error rates?
They did basically what I don't know exact details of it. So lots of grains of salt here, but I think what they did is random L1D flushes. Yeah.
One more question. Well,
maybe a bit of a philosophical question here. Would it be the case that the industry has to rethink on the hypervisor architecture because of these issues?
Yes, I do think that they are. So, for example, the mitigations I just listed are kind of hypervisor redesigns a bit, because it's really changing the whole layout of the virtual address space of hypervisors. The hard thing is that many of the hypervisors we know of now, so for example Linux, is just one big monolithic kernel. So it's super hard to compartmentalize it and such. But in general, you could say this is just the trivial, like, try to give everything least privilege possible, right? A microkernel would have been safer. So I think from the design perspective, this is now more forcing people to start doing the massive amount of work to redesign these monolithic kernels into more compartmentalized pieces for security.
Thank you.
thank you. So shall we conclude, or we have another question? No? All right. Thank you, Mathé. Let's